Welcome to section 1.7 part 2 mathematical proofs. Today we are looking at indirect proofs. This is Dr. Gilbert Eyabi. In part 1 we looked at direct proofs. The goal is to prove that P implies Q. So we assume or we suppose that P is true. Then we use definitions and axioms and lemmas and propositions to prove that Q is true. Straightforward, beautiful. But as we shall see very soon, there are some conditional statements where direct proof may not go as nicely as we would want it to go. So what we do then is we use indirect proofs. The first would be contraposition. Recall that P implies Q is equivalent to not Q implies not P. In fact, we say that the contrapositive of P implies Q is not Q implies not P, i.e., if we are required to prove that P implies Q, if we can prove that not Q implies not P, then we would conclude P implies Q, and that is known as proof by contraposition. Let's go ahead and take an example. Prove that if n is an integer and 3n plus 2 is odd, then n is odd. If 3n plus 2 is odd, then n is odd. Now, I'll give you my proof because I want to start with a direct proof and show you why we are switching to an indirect proof. A restatement of the problem. Prove that if n is an integer and 3n plus 2 is odd, then n has to be odd. Proof. Let's attempt a direct proof. Suppose n is an integer and 3n plus 2 is odd. We are required to prove that n is odd, i.e., we want to prove that there exists an integer k such that n equals 2k plus 1. K has to be an integer. But 3n plus 2 odd, what does that mean? It means there exists an integer k1 such that 3n plus 2 can be written as 2k1 plus 1. We are interested in n, so we're going to solve for n. If you move 2 to the right hand side, that gives us 3n equals 2k1 minus 1 and n equals 2k1 minus 1 divided by 3. Can we write this as 2k plus 1 where k is an integer? If k were just a real number and not necessarily an integer, yes, we can always do this. We can always find a way to write this as 2 times some number plus 1, but we need k to be an integer. We don't even know what k1 is. We only know that k1 is an integer. So 2 times k1 minus 1 divided by 3, is that necessarily an integer even? No, it may not be. In fact, you can find an integer k1 such that 2 times k1 minus 1 divided by 3 is not an integer. N has to be an integer. Officially, we're stuck. Do we start crying? Okay, we cry for a while, then we stop and we say, wait a minute, there is something called indirect proofs. And this time around, we are interested in proof by contraposition. So we shall provide a proof by contraposition and show that, remember, the contrapositive of 3n plus 2 odd implies n odd would be n even implies 3n plus 2 even. So we're going to use a direct proof on the contrapositive of P implies Q. And if we can prove that to be true, then we can assume that our original problem, P implies Q, is true and we're done. So suppose n is even. We are required to prove that 3n plus 2 is even. But n even means there exists an integer k1 such that n equals 2k1. Therefore, 3n plus 2 would be 3 times 2k1 plus 2. I have a 2, so I can pull out my 2, factorize out 2, and I'm left with 3k1 plus 1. I set all of this to be my k wiggle, and this k wiggle is the k I'm interested in. It is an integer. So k wiggle is 3k1 plus 1, and I claim that is an integer. Why is it an integer? 3 is an integer, k1 is an integer, the product of two integers is an integer, the sum of integers is an integer, so my k wiggle is an integer. So what have I done effectively? I did prove that 3n plus 2 equals 2 times some integer k. And my k in this case is my k wiggle, which is 3k1 plus 1. Therefore, 3n plus 2 is even. Hence, my original problem holds, i.e., if n is an integer and 3n plus 2 is odd, then n is odd. Done. That is proof by contraposition. We use the contrapositive of P implies Q to prove that P implies Q. Let us look at some more examples. Example 1. Prove that if n is a positive integer and 7n plus 4 is even, then n is even. Again, we are concentrating on this last part. You want to prove that if 7n plus 4 is even, then n is even. Number 2. Prove that if n is an integer and n cubed plus 5 is odd, then n is even. Follow the exact same procedure that we used here. State first of all the contrapositive of the statement P implies Q, and then use direct proof on the contrapositive, and then conclude P implies Q. And for both problems, I want you to use proof by contraposition. Proof, I'm going to leave it as a SIVS, simple exercise for serious students. So go ahead and give a shot at these two problems. Again, I would expect you to provide the proofs of these problems when you submit your content summaries for 1.7 part 2. Beautiful. Let's proceed. Next example. Prove that if n is an integer and n squared is odd, then n is odd. Again, if you follow the procedure we used in the previous problem, you'll quickly run into some difficulties, and then you have to prove it by contraposition, in which case we'll be proving that if n is even, then n squared is even. Again, I'll leave that for you to execute. I'll prefer that you write your own proof and not just follow what is written here. The next indirect proof we would be interested in is proof by contradiction, aka reductio ad absurdum, proof by contradiction. Now, this is how I want you to view proof by contradiction so you don't get confused with all these many statements. If you are asked to prove that P implies Q, you actually start off by supposing that P is true, okay? You want to prove that P implies Q, so you suppose that P is true. And then you assume, in the contrary, that Q is not true. Then you arrive at some contradiction. And as you would see throughout your study of mathematics, the contradiction could be anything. The easiest and the most common of the contradictions would be you coming back to contradict the hypothesis P. But it could be a contradiction which hits against a mathematical fact, a known fact. Once you arrive at that contradiction, you say, this is a contradiction. And the contradiction arises because we did assume that Q is not true. Therefore, Q is true. At times, it could be as simple as arriving at the conclusion that 5 equals 7. You say, and this is a contradiction. This contradiction arises because we did assume right from the beginning that Q is not true. Therefore, Q has to be true. In other words, there is nothing like a middle way between true and not true. Q is either true or is not true. So if you assume that Q is true and arrive at a contradiction, then that means Q has to be true. Therefore, we would have proved the conditional statement P implies Q. Let us look at an example. Example, prove that if you pick 22 days from the calendar, at least 4 must fall on the same day of the week. Well, let's go through that proof, and I would prefer to do it in my own way. Okay? So, suppose 22 days are picked. Remember, the question says if you pick 22 days, that is your P, implies at least 4 must fall on the same day. So P implies Q. You pick 22 days. You want to prove that at least 4, which is greater than or equal to 4, that's what at least means, would fall on the same day of the week. So suppose P is you picked 22 days. Now assume on the contrary that at least 4 does not fall on the same day of the week. What does that mean? It means at most 3 would fall on the same day of the week. Now, since there are 7 days of the week, that means we did pick at most 21 days from the calendar. But how many days did we pick? 22 days. So this contradicts the hypothesis that we picked 22 days. Once you arrive at a contradiction, this is how you conclude. You have to write that out. This contradiction arises from the assumption that at least 4 does not fall on the same day of the week. Therefore, we would conclude that at least 4 would fall on the same day of the week. End of proof. We would look at more mathematical proofs by contradiction, and you see exactly what we are doing here. The whole idea is we suppose that P is true, assume that Q is not true, and then use definitions and theorems and lemmas and propositions and arrive at a contradiction. Then we conclude that the contradiction is because of our assumption that Q is not true, therefore Q has to be true, and then we end the proof. Another example using proof by contradiction. I need you to prove that the square root of 2 is irrational. Now recall above that we did prove that if n squared is even, then n is even. Use proof by contraposition. In other words, just prove that n odd implies n squared is odd. We would use this here, that's why I have it here. So make sure that you know how to prove that if a squared is even, then a has to be even using contraposition. Now, let's go ahead with our proof. Suppose on the contrary, root 2 is rational. Then that means there exist integers a and b different from 0, and no common factors between a and b, such that the square root of 2 equals a divided by b, i.e. what we are saying is if the square root of 2 is rational, then I can write it as a fraction in its simplest form, where the only common factor between a and b is 1 and nothing else. Okay? Now, if root 2 equals a over b, then I can square both sides and I end up with 2 equals a squared divided by b squared, and simple solving would give me 2b squared equals a squared. But what this means is that, look at this very carefully, a squared equals 2 times some k. b is an integer, the product of two integers is an integer, so b squared is some k wiggle. So that means a squared equals 2 times some k wiggle, i.e. a squared is even. A squared is divisible by 2, but a squared even means that a is even. What does it mean for a to be even? It means there exists some integer c such that a equals 2 times c. Bring all of this back into this equation. That will give us 2b squared equals a is the same as 2 times c. So that will be 2 times c squared, which will give us 4c squared. I can cancel 2 on both sides, and I'm left with b squared equals 2 times c squared. Again, c is an integer, c squared is an integer. So this is the same as b squared equals 2 times some k wiggle, where our k wiggle here is c squared. In other words, b squared is even. But b squared even right here implies that b is even. Hey, wait a minute. A is even, b is even. That means 2 is a common factor of a and b. 2 divides a and 2 divides b. Wait a minute. Didn't we just say that if the square root of 2 were rational, then I can write it as a divided by b, where b is different from 0, and there are no common factors between a and b except 1. So I have just arrived at a contradiction, because I have realized that if root 2 could be written as a divided by b, then there is actually a common factor between a and b different from 1, and that common factor is 2. This contradiction arises because of our assumption that the square root of 2 was a rational number. Therefore, we can conclude that root 2 is irrational, and that ends our proof. This is actually a very standard problem in math. You would probably see it again in abstract algebra and in some other places. proving that the square root of 2 is irrational. As a matter of fact, the square root of 3 is also irrational. The square root of 7 is also irrational. The square root of 11 is also irrational. Do you see anything common between those numbers I've just mentioned? Yes. As a matter of fact, the square root of p is irrational if p is a prime number. In Math 420, abstract algebra, I would expect you to actually prove that the square root of p is irrational if p is prime. But for now, I would leave that for the future. You should at least be able to prove that root 2 is irrational, and I think you've just done it. Good job. Here is another very standard problem in math. We're going to see this same problem again in Math 420, abstract algebra, just like the problem before it. It says, prove that there is no largest prime number. You know, there is a quest to find the biggest prime number. Well, people are moving on with the quest, and each year we get bigger and bigger and bigger prime numbers. Is there a prime number that is bigger than every prime number that exists? No. And the proof is actually very exciting. In Math 420 abstract algebra, I'll give you a very formal, beautiful proof. But here we're going to be excited with the proof the way it is. That's good enough for this class. So assume on the contrary that there is a largest prime number. And let's call the prime number Pn. Then we can list all the prime numbers from 2 right up to Pn, and that will be 2, 3, 5, 7, dash, 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 right up to Pn. Let's go ahead and define a new number, R, which would be the product of all the known primes times the biggest prime on Earth. That is the biggest of all the primes. There is nothing bigger than it. So define R to be the product of all the existing primes plus 1. Then obviously you can see that R is going to be greater than 1. Now, none of the prime numbers on this list divides R because we have a plus 1. So none of these would divide R. So you cannot say that any of these would be a factor of R. By the fundamental theorem of arithmetic, which we shall see in chapter 4, R as it is defined is either a prime number or it has a prime divisor. Let's talk about it again. R as defined is either a prime number or it has a prime divisor. All of that would come from our studies of the fundamental theorem of arithmetic, but we will not go into depths right now. But if R is prime, what have we done? We have found a prime number that is not one of the primes P1 up to Pn. That contradicts our assumption that Pn was the largest prime. Now, if R is not prime, there exists a prime that divides R. And because none of these primes here would divide R, that prime number that would divide R is going to be different from these. What does that mean? That means it's bigger than all of these. And again, that contradicts our assumption here that there exists a largest prime called Pn. So we conclude that there is no such thing as a largest prime number, and we're done. Like I mentioned before, the proof is wonderful the way it is in this class, but I'm going to give you a very formal proof as we move on, especially in abstract algebra. Again, it's one of the standard problems in math, and we expect that at least at this level, you should have a little taste of two of the standard problems in mathematics. Now, a couple of theorems or problems you would see would be biconditional statements. If I ask you to prove a biconditional statement, what do? And after this, we shall look at equivalence to prove that the following statements are equivalent. How do we handle such proofs? Example, prove that if n is an integer, then n is odd if and only if n squared is odd. It's going both ways. Prove that n is odd if and only if n squared is odd. So what we do is we prove the forward direction and then we prove the backward direction. And at times, one direction might go with a direct proof and the reverse direction might go with an indirect proof. For example, for this problem, we want to prove that n odd if and only if n squared is odd. The forward direction would be Suppose n is odd. We prove that n squared is odd. That will be direct proof. The reverse direction would be if n squared is odd, then n is odd. And we prove that using an indirect proof. You could use either contraposition or contradiction. So that is how we handle bi-conditional statements. We prove the forward direction and the reverse direction. And we can use direct or indirect proofs on either of the directions. And that is when we say you're getting mature in proofs. Now, before I leave this portion, I should also mention proofs that involve the word the following are equivalent. If I ask you to prove that the following are equivalent and I give you statements A, B, C, D, what you do is you prove that A implies B, B implies C, C implies D, and D implies A. That is how you prove statements of the form the following are equivalent. You prove that the first one implies the second implies the third implies the fourth implies the first. If you go in circle, then you can assume that the problem has been solved or the proof of the theorem has been executed. Now, let's proceed with an interesting problem. Here is an attempt to prove that 1 equals 2. Of course, if you can prove that 1 equals 2, then the whole math world would crumble. So we start off with A equals B. That's our premise. Okay? And we multiply both sides by A, and we arrive at A squared equals A times B. And we subtract B squared from the left on both sides, which is a good mathematical procedure. We arrive at A squared minus B squared equals A times B minus B squared. And the difference of two squares, so this factorizes out as A minus B, A plus B. And over here, we can factorize out B, and we are left with A minus B. And then we cancel A minus B on both sides. We are left with A plus B equals B. And that simply means since my A equals B, the A plus B will just be 2B equals B. And if I cancel out my B, I'm left with 2 equals 1. So did I just prove that 1 equals 2? No. There are so many little errors here or assumptions, but steps 4 to 5 is very major. We just divided both sides by A minus B. We do not know that A minus B is different from 0. As a matter of fact, A minus B equals 0 because A equals B. You cannot divide by 0. That is a no-no in mathematics. And so this entire proof crumbles. Okay, you should be able to locate problems like this in proofs. Looking ahead, now let me just say this. When you are given a problem, a proof problem, your first attempt is always direct proof. If direct proof does not work, then you either go to contraposition or to contradiction. I would propose contraposition first, and if you get stuck somewhere, then you might want to try contradiction. But contradiction is wonderful. As you would learn in abstract algebra, in advanced calculus, you never really go wrong with proof by contradiction because all you do is find a contradiction, which could just be anything. It could be like arriving at the conclusion that 1 equals 2. You say this contradiction arises because of our assumption that not P, because of our assumption that not Q, therefore Q, and we're done. Okay? Now, looking ahead, if direct method of proofs do not work, we may need a clearer use of a proof by contraposition or a proof by contradiction. In the next section, we will see strategies that can be used when straightforward approaches do not work. That would be section 1.8. And then in chapter 5, we would see what is known as mathematical induction. That's another proof technique. We may not exhaust it in this class. This is discrete method. We have a lot of things to do. But in advanced calculus, in abstract algebra, we would really go deep into mathematical induction. And if we have time in chapter 6, we might even look at some combinatorial proofs. That's interesting. So I look forward to seeing you in section 1.8, some proof methods and strategies. Thank you for watching section 1.7 part 2. God bless you, and I look forward to seeing you in section 1.8, where we start looking at some proof methods and strategy. Thank you.